Welcome to our comprehensive overview of commercial carbon capture and storage works as a vital strategy for heavy industry decarbonization. In this 10-minute video, we will explore how this technology works, why it is essential for the global economy, and the economic frameworks making it a reality in 2026. As the world moves toward aggressive net zero targets, the challenge for heavy industry is unique and daunting. Unlike light manufacturing or passenger transport, sectors like steel, cement, and chemical production cannot simply switch to batteries or renewable electricity for their primary processes. These industries require intense high-temperature heat and often produce carbon dioxide as a direct byproduct of chemical reactions. For these sectors, carbon capture is not just an elective environmental choice, but a fundamental requirement for their continued existence in a low-carbon world. To understand the strategy, we must first look at the capture process itself. Carbon capture happens at the point of emission, usually at a large industrial facility. There are three primary technical pathways for capturing carbon. The first is post-combustion capture. This is the most mature technology and is often used for retrofitting existing plants. In this process, the exhaust gas or flue gas is passed through a chemical solvent. This solvent, usually an amine-based liquid, specifically binds to the carbon dioxide molecules while letting other gases like nitrogen pass through. The solvent is then heated in a separate chamber to release the pure carbon, and the solvent is recycled back to the start. The second method is pre-combustion capture. This is primarily used in power generation and hydrogen production. The fuel is processed into a mixture of hydrogen and carbon dioxide before it is burned. The carbon dioxide is removed at this stage, and the hydrogen is used as a clean-burning fuel. The third method is oxy-fuel combustion. Here, the fuel is burned in pure oxygen instead of air. This produces an exhaust stream consisting almost entirely of water vapor and highly concentrated carbon dioxide. The water is easily cooled and removed, leaving a stream of carbon that is ready for transport. Each of these methods has different costs and efficiencies depending on the specific industrial application. Shutterstock. Key fit. Once the carbon is captured, it must be prepared for transport. This involves compressing the gas until it reaches a supercritical state. In this state, the carbon has the density of a liquid but the viscosity of a gas. This makes it much more efficient to move through high-pressure pipelines. For long distances or offshore locations, we are seeing a massive increase in the use of specialized carbon carrier ships. These ships function similarly to liquefied natural gas tankers. The vision for 2026 involves the creation of industrial carbon hubs. Instead of every factory building its own storage site, multiple companies in a single region will feed their captured carbon into a shared pipeline network. This sharing of infrastructure significantly lowers the barrier to entry for smaller industrial players. The next critical step is storage, which is also known as sequestration. The captured carbon is injected deep underground into carefully selected geological formations. These sites are typically located more than 1 kilometer below the surface. We primarily use depleted oil and gas reservoirs or deep-sealing aquifers. These rock layers are porous like a sponge and can hold vast amounts of flue. Crucially, these storage sites are covered by an impermeable layer of rock called a caprock. This acts as a permanent seal to prevent the carbon from ever escaping back to the surface. Over decades and centuries, the injected carbon undergoes various physical and chemical changes. It dissolves into the salt water present in the rock and eventually reacts with minerals to turn into solid carbonate rock. This ensures that the carbon is removed from the atmosphere permanently. We must now discuss the economic strategy that makes commercials viable. For a long time, the biggest hurdle for CCS was the cost. It is an expensive process that requires significant energy and specialized equipment. However, the landscape has changed due to government policy and carbon markets. In the United States, the 45Q tax credit has been a massive driver of investment. It provides a fixed dollar amount for every ton of carbon that is successfully captured and stored. This turns a waste product into a source of revenue for industrial companies. In Europe, the emissions trading system places a high price on carbon emissions. When the cost of paying for carbon permits becomes higher than the cost of capturing the carbon, CCS becomes a rational and necessary business decision. Furthermore, heavy industry is seeing a shift in consumer and investor demand. Companies that produce green steel or low-carbon cement can now charge a premium for their products. Many large construction projects and automotive manufacturers are willing to pay more for materials with a lower carbon footprint to meet their own sustainability goals. This created a new market for decarbonized commodities. Financial institutions are also looking at carbon intensity as a major risk factor. Companies that fail to implement a decarbonization strategy like CCS may find it harder and more expensive to secure loans or attract investment in the future. Therefore, CCS is being integrated into the core corporate strategy of global industrial giants. However, the road to full-scale commercialization is not without challenges. The first is public perception and safety. While geological storage is backed by decades of data from the oil and gas industry, some communities are concerned about the integrity of storage sites and the safety of pipelines. Providing transparency and ensuring rigorous monitoring is essential for gaining public trust. Modern storage sites use advanced sensors and satellite imaging to detect even the slightest movement of carbon underground. The second challenge is the energy penalty. Capturing carbon requires energy, which can reduce the overall efficiency of a factory. Researchers are working on next-generation membranes and solid sorbents that require much less heat to release the captured carbon. Scaling the infrastructure is the third major hurdle. To meet climate goals, we need to scale the current capacity by a factor of 100 over the next few decades. This requires a massive mobilization of capital and a